Okay. It's Friday, yay. Okay. All right. We're all happy it's Friday, and we're excited to learn about concavity. Okay, so concavity is the term used to describe the increase and decrease of the slope of the tangent line. So we use, and this is confusing, we use the first derivative to determine the increase and decrease of the function, right? Now we're using the second derivative to describe the increase and decrease of the first derivative, all right? And that'll make more sense, hopefully, here in a second. All right, so we talked about concave up means something like holds water, so it's like goes up, and if it empties water, it's concave down. So this would be concave down. Okay, so, and the rule here is that if you have a function f of x that's differentiable on an interval, again, that just means nothing big is happening on that interval, right? No cusp, no corners, etc. It's kind of a smooth interval. Then it's concave up if the first derivative is increasing on the interval, concave down if the first derivative is decreasing on the interval. Let's kind of step away from that for a second, all right? But that's going to be our ultimate test. But let's look at this graph right here. So if we were to talk about the tangent lines, if I were to draw some tangent lines, these tangent lines are negative, right, at this point. And I'm just going to kind of assign them some values. Let's say this is like a negative 2, and then we're getting a little flatter, so let's say negative 1. And these are still negative, but flatter still, right? So maybe negative 1/2. What's the slope of this tangent line? 0. And now over here, how does the tangent line change, the slope of the tangent line? It's now positive, but still low, right? Like maybe positive 1/2. And then maybe this is maybe positive 1. Okay? So all along here, the slopes of the tangent line are they increasing or decreasing? We're going from -2 to -1 to 0 to 1/2 to 1, right? They're increasing. So M is increasing. Okay? Now I'm going to make a point right here. Just draw a point. Now let's look at the slopes of the tangent line after that. Let's say this is, let's say it's positive, I don't know, 3. No, let's say 2. And now this is still positive, but it's a little flatter, right? So let's say that might be M equals maybe 1/2. And up here, M is it's flat, so M equals 0. Does everybody agree with that? And now what happens to the slopes of the tangent line? They're decreasing. So let's say this is a little flatter. Let's say negative 1/2, negative 1, etc. So as of this point, what's happening over here? Are the slopes getting higher or lower? Increasing or decreasing? Just the blue slopes. They're decreasing, right? So the function is increasing this whole time on this interval, like from the bottom, from the min to the max. But at this particular point, this red point, the slopes start decreasing. So M So this red point that I pointed out is actually where concavity is changing, where the function is going from concave up to concave down, right? The function itself at this red point didn't stop increasing or decreasing, but the concavity of the function did, okay? So, and this is where this is what we're going to find is a critical number of the second derivative. Critical numbers of the first derivative, remember, show us a min or a max where the function stopped increasing or decreasing. Critical numbers of the second derivative show us where concavity changes. Okay, and that is the second derivative is going to tell us that. Okay, does that make sense? So the first derivative we could tell us when we could use to find out about whether the function was increasing or decreasing. Second derivative, we talk about whether the first derivative is increasing or decreasing. Okay, and I promise we don't go any farther than that. We don't go into the third derivative. So let's talk about concavity for just a second. So the test we're going to do is if the second derivative is greater than 0, which again is just another way of saying positive, on an interval, then the graph is concave up. If the second derivative is negative, or less than 0, on an interval, then the graph is concave down. So sound familiar? Where we're just trying to find positive or negatives and using those to say whether it's up or down. Now, the place where the graph switches concavity, and this is actually going to be our type of critical number for the second derivative, is called an inflection point. So instead of a max or a min or an extrema, we're looking for inflection points. So on my previous graph right here, this would be an inflection point. Okay. Okay, makes sense, kind of? Examples will make it a little more clear. Now, the one thing you want to make sure of, don't confuse the concavity of a curve with increasing or decreasing. And this gets a little tricky. So if you look at this function is increasing, right? The y values are getting higher, and it is concave up. In other words, it would hold water, right? The slopes of the tangent lines are going from negative to 0 to positive. This function is also increasing, right? The y values are going up, but it's actually concave down, right? Because so it would like dump water. Dump was the word. It would dump water. Does that make sense? And the slopes of the tangent line are actually getting lower, right? Because it's going up, it's going to go 0, it's going to go down. Okay, are you going to go charge? Oh, you're not going to make it. Okay. There you go. Okay, now we can look at the same examples for decreasing. Again, this function is decreasing, right? But it's concave up. It would hold water, right? The slopes of the tangent lines are getting lower. They're going from actually they're increasing because they're going from negative slopes to 0. This function is actually decreasing and it's concave down. It would dump water. Okay? Does that make sense visually? Okay, so the homework actually in the book is just actually looking at graphs and determining what part of a graph is concave up and concave down. Okay? So the steps that we're going to use to use concavity on a function are really almost identical to what we did with the first derivative, except now it's the second. So we're going to find the second derivative. We're going to find where the second derivative is equal to 0 or the second derivative does not exist. Sound familiar? We're going to use the number line test for the second derivative and label concavity for each interval. And then we're going to plug in appropriate x values into the original function to find the inflection points. Huh? Sure, yep. So everything we did use the first derivative for, now we're going to use the second derivative for. No, I mean the original function. Yeah, no, good point. You good? Okay. All right, so first I'm going to do this example. Eventually, we're going to do a couple examples where we're going to do from start to finish. But on this first one, I just want to find out, on this interval, just want to find out where concavity changes. All right, so I'm just going to find out, and then we're going to look at the graph, and it should make some sense to you. So I'm not going to do all of our stuff with the first derivative that we normally do. We will in next examples. Right now, I'm just going to say, okay, I got this graph. I just want to know where it changes from concave up to down. So I need to find the second derivative, right? So I'm going to take the first derivative, and I get 12x to the third minus 6x squared minus 24x plus 18. I'm not going to do anything with it because, again, I'm not going to try to find max and mins right now. I just want to see where concavity changes. This is a pressing need for some reason. So let's go ahead and take the second derivative. And I'm going to, I get what, 36x squared minus 12x minus 24. So I found my second derivative, and now, again, I want to find out where concavity changes, so I'm going to set it equal to 0 and solve. So what can I do here? Take out a 12. And I get, what, 3x squared minus x minus 2. What's that? AC method, right? So what multiplies to negative 6 adds to negative 1. Negative 3, yeah, sorry. I'm ready for the weekend, I think. Negative 3 and 2. So then we get 3x squared minus 3x plus 2x minus 1. Split it down the middle. Take out a 3x. Gosh, what's that? Minus 2. Hang on, what did I do wrong? Oh, minus 2 here. There you go. I told you. Let's see. Okay, so this is minus 2. And then I can take out a 2, and I get x minus 1. So I've got 12 times 3x plus 2 times x minus 1. Thank you, Louie. I needed assistance there. So my critical numbers for my second derivative, or my inflection points, are going to be x equals negative 2/3 and 1. Everybody agree with that? Okay. You good? Okay, so again, just like last time, I'm going to start a little number line, and I'm going to put negative 2/3 and a 1. Okay. And now again, I need to find out. I'm looking for whether the slopes of the tangent lines are increasing or decreasing. So my second derivative test says that if any of these numbers, if the second derivative is positive for any number in this interval, then the slopes of the tangent lines will be increasing and it will be concave up. And this interval and that interval. So the same kind of thing. We're just going to pick a number, plug it into the second derivative, see if it's positive or negative, and that'll tell us the concavity of that interval. Okay? So let's choose something less than negative 2/3. So negative 1. So I can use the same kind of shortcut method with my factors. So negative 1, I'm going to have a 12, a positive out here. Negative 3 plus 2 is going to give me a negative number. Negative 1 minus 1 is going to give me a negative number. So so it's positive, right? Okay, so the tangent line slopes are increasing in that interval. Between negative 2/3 and 1, I can choose 0. So I've got a 12. 0 plus 2 is going to be positive. 0 minus 1 is negative. So I get a negative. So concavity is negative for that interval. And I've got f of 2, let's say. I've got 12. I've got 6 plus 2 is positive. 2 minus 1 is positive. So I've got positive. So I know concavity for this equation, for the function, is positive until it gets to negative 2/3, then concave down, then concave up. Okay? Now let's actually take a look at this. Well, okay, yeah, let's take a look at the function first. All right, so if I take a look at this function, again, this is all about the original function. So we want to take a look at, I'm going to graph the original function here. That's not what I wanted. So I get 3x. This is so hard, so much harder on this than it is on the handheld one. 3x to the 4th minus 2x to the 3rd. I'll make sure I'm typing in what I think I am. Minus 12x squared plus 18x plus 15. Now, if I graph it. All right, now I'm going to zoom. What do I do here? I'm going to zoom. Hang on a second. Hang on, Katie. Okay. Okay, so if we look at this function on the calculator, we can see, and we're saying what we found is that we're saying, according to our work, that inflections change in negative 2/3 and at 1. And if you look at it on the calculator, again, you can see where this is a min, which we didn't care where that was happening. The negative 2/3 would be like right in here, and it's changing from concave down to concave up, right? I'm sorry, concave up. And then here it's going to concave down, and then it's changing to concave up. Does that make sense? So there wasn't even really a relative min or a max even right here, but concavity still changed. So it's concave up along here, negative 2/3 is about right there, changes to concave down, and then at 1, it's changing to concave up again. Okay, does that make sense? Now, if we want to find out at negative 2/3 where to actually graph that point, we would want to do what? Plug in negative 2/3 into what? Into the, not the first derivative, but the original function, okay? And actually, let's go ahead and do that real quick. So if we plugged in negative 2/3, I'm just going to use the calculator for that. So we plugged in negative 2/3 into the original function, and we now know our inflection point is negative 2/3 and then negative 1, what was that? Negative 1.15, we'll say. Okay? And now if we want to, so now we also would want to know what the value at 1 would be. So our other inflection point would be 1. And if we plug that into the original function, that's a little bit easier, because we're basically just going to have 3 minus 2 is 1, minus 12 is negative 11, plus 18 is, what, 7, plus 15, 22? Does that make sense? Okay, so those are our inflection points. We didn't look at anything else on the graph, but we know that that's where concavity is changing. Okay? Thrilling stuff, right? Well, yes. Yes. So now what we're going to do, we're going to skip this next one, because again, these examples just go on forever. I kind of bore myself after a while. So we're going to do just a couple examples of what your homework's going to look like. Yeah. Okay? So here's the big finale, like the crescendo or whatever of the whole chapter. So we're going to take one function, okay, and we're going to determine where it's increasing and decreasing, and where it's concave up or down. Find the relative extrema, the mins and the maxes, the inflection points, and sketch the graph. Okay? And we're also going to use the y-intercept for each. Okay? So we're going to do 2 of those, and then that's what your homework's going to look like. Okay? So your homework, is going to be the book problems, and then you're just going to use these two that you're going to do what we're going to do right now for these two problems, okay? All right, so so we're going to first take the first derivative and process it through, right? Find the mins and max, etc. Then we're going to take the second derivative, find the inflection points, then we're going to throw it all on a graph, okay? All right. So, first derivative, 6x squared plus 6x minus 12. Now, the good news is we only do these for like nice polynomial stuff. We're not doing them for the uglier functions. Set it equal to 0, and we need, and how do we factor it? We take out 6, right? Well, so the last example I did, we were just looking for inflection points. Okay, so we just jumped right to second derivative and processed that. Now we're going from start to finish. Okay, so we're going to take the first derivative, do all the old stuff we did with that, and then we're going to take the second derivative. Okay? All right, so we take out a 6, we get x squared plus x minus 2. This factors to what? X plus 2 minus 1. Right with me? And so our critical numbers are negative 2 and 1. So these critical numbers are going to represent what on a graph? Did I do something? What's that? Well, again, we're going to take the first derivative and do everything we have done on it. Then we're going to take the second derivative. Okay? So the last example, we just kind of jumped to the second derivative. Okay. But this is from start to finish. This is what your homework's going to look like. Does everybody understand that? Okay. So these critical numbers from the first derivative are going to eventually tell us what for our graph. Increasing, decreasing, and mins and maxes, right? Okay. So again, this is all stuff we've already done. So but we're going to do it one more time. All right. So again, how do we find out whether this is increasing or decreasing? Right. Pick a number. So let's pick like -3. And if we plug it into our first derivative, we're going to get a plus, a negative, and a negative. So it's increasing there, right? So it is, okay, so it's increasing. What number do we want to choose for here? 0. Plug it in, we've got 6 is positive, 0 plus 2 is positive, 0 minus 1 is negative. So we got negative. Second interval, we can choose what, 2. And we get a positive, and a positive, so it's positive. So what's happening at -2? It's a max, right? So we have a max at -2. And what do we have at 1? A min at 1. Now, again, because we're eventually going to graph these, we have to find out the of part, right? So what's the y value of those? And to do that, we plug those into the original. Okay. So let's do that real quick. Actually, I'm just going to do that on. So to save some time here, I'm just going to do that on my calculator real quick. I got 13. Did anybody else do that? Did you get 13? Okay. All right, so -2 is a max of -2 and a 13. And then 1 is going to be 2 plus 3 is 5 minus 7, -7, so -14. Okay, now, so we're going to hold off. So these 2 points, we will eventually graph. Okay, those are, we're going to actually graph those, and those are mins and maxes we found from the first derivative. Now we're going to take the second derivative and find inflection points. So now we go to the second derivative, and we get 12x plus 6. Everybody with me? Set it equal to 0. This one's a little bit easier, right? We solve. We get 12x equals negative 6. So x equals what? Negative 1/2. Okay. So we draw another little number line, because this number line, this is all about concavity now, right? So we know we have an inflection point at negative 1/2. So we know concavity is changing at negative 1/2. You want to find out which way, right? So we choose something that's less than negative 1/2. So let's say negative 1, and we're going to plug negative 1 into our second derivative, right? And we're only interested in whether it is positive or negative, right? So negative 1 gives negative 12 plus 6 would give us negative. And then we can choose 0, right, for our second one. And it would be positive. So we know we have an inflection point at negative 1/2 of, and we need to plug in negative 1/2 where? Into the original. Yes, yeah. And I get negative 0.1/2. So this again, so this again is a point I'm going to put on my graph. Okay? Now, okay, now we're going to just draw a big graph and sketch the function. Okay, so we come up here. I know I need a point at negative 1/2 and negative 1/2, right? Let's see, let me give some numbers here. So we're going to go to, let's see, so we need a y-axis of 13 and negative 14. So we'll just make up those a little bit. Okay, so I get an inflection point of negative 1/2, negative 1/2. Right, so that would be right in between negative 1, negative 1. I need a max of negative 2, 13. So negative 2, and I'm just going to label this 13. That I can, negative 2, 13. And I'm going to label this one. So I have 1, negative 14. So I'm going to label this negative 14. Okay. So I know, so to connect those points, I know I'm going to go up to negative 2, then down to 1, and then up. And I know that my concavity should be changing right at that negative 1/2. So I can draw my function. Like that. So inflection points are definitely harder to see right away, you know, or harder to identify just looking at a graph, but it should be somewhere, you know, like oftentimes within a min or a max. We're going to look at some that are a little bit different, that they're not as obvious. Okay, that makes sense? All right, I want you guys to try that on the next one. Okay, so this is an x to the fourth. So instead of me talking through the whole first derivative, I want you all to go ahead and do the first derivative, try to take it from start to finish, okay? And then we'll go over it. Okay, so we found all this, and we found critical numbers of 0 and 3. So we're going to plot 0, 0 on the graph. Then you took the second derivative, and again, found critical numbers of 3 and 1. So you have 3 is happening again, right? And we found out that concavity is positive, negative, and then positive. And our inflection points are 1, 11, and 3, 27. So I'm going to plot 1, 11, and 3, 27. Okay. Now we know. So, and we know from our first derivative, it's increasing, coming into 0, right? And then, decreasing, coming into 0, then increasing, and then our concavity changes from negative to positive at 3. So here you come. It's hard to draw. Really, I'm not great at this, but you kind of picture that it's going negative concavity. In other words, that would be like dropping water. And then it changes to positive concavity. So it's not a max, right? It's just an inflection point. So it's just kind of a subtle change from negative concavity to positive. Right, and then negative, positive. Yes, negative, positive, positive. Yep. Exactly. Yep. So this is just an example. So concave on our normal ones, like when we were doing the polynomial ones, where it was always positive, negative, like this, concavity was pretty obvious, right? Like down, up, down. But an inflection point is more meaningful when it's something like this, where it's still increasing. It's just subtly kind of changing. Yep.
Wait, I didn't get positive graph.
On the left?
Yeah.
Did you get 1 and 3?
Yeah, I got 1.
Did you, on which one? And then, oh, but on 3, you got positive, you got okay. Let's see, I'm plugging the factor point.
Oh,
yeah, so I think that's easier than trying to plug it. Uh-huh.
I guess so 4, it's positive, negative, positive, right?
On concavity.
Yeah. So on the graph, so it's positive, negative, 1.
Yeah, positive going to 1. Let's see. 1, 11. Positive going up to 1. And then, oh, hang on, did I draw it wrong? So positive up to 1. Yeah, hang on. 1, 11. So positive going up to 1, then negative, then positive. Make sense? So concavity all the way up to 1 is positive. So it's almost like a parabola coming up to 1. Then between 1 and 3, it changes to negative. Is that what you were talking about? Then it goes positive again. Yeah, I've kind of drawn it. I've put an inflection point in there. What's that? This is positive concavity, right? Well, I'm not actually, I'm not, the function's not ever decreasing. So this shouldn't be, no, I shouldn't be dipping. I shouldn't be making any kind of, like, it's still going continually up. It's just changed from this way to this way. Well, again, the the function itself is decreasing, increasing, and increasing. Okay, so this tells you about the function. The concavity is positive until you get to 1. So here's my line at 1. Okay, so it's positive. Yeah, this, my line at 3 is negative and then positive. Right, more like just a little swoosh kind of thing. Okay, questions about that? All right, so that is what you want to do on the 2 problems that I gave you. Okay, you want to take it start to finish like this. Does that make sense? Am I good? So the graph will look like this. So we're going to have, a min at 0, 0. At 1, 11, we have an inflection point. And at 3:27, we have an inflection point. Now to draw our graph, it goes increasing and concave up. It goes decreasing and then increasing, concave up, and then it switches to still increasing but concave down, and then still increasing but concave up. So it should look like that. So I hope that's clear. And now the 2 homework problems, you want to do this whole process that we did from the first derivative through the second derivative. Okay, thanks. Bye.